Okay, good day. This is Pre-Calculus. I'm Mr. McCully, and this is the third and final part of probability lesson 44C. Let's get right to it. Today we're going to have the same goals as we had in the last two videos, but this one is going to get into some of the more complex probabilities where we start using the counting principles that we learned from the last lesson, 43, to calculate some of these probabilities, especially when the outcomes and the sample spaces start to get very large. So I'm not going to go through all of the notes. We've done that twice now. So I'm going to get right to some problems here. And the first example that I got today is going to be two integers are chosen from 1 to 40 by a random number generator. What is the probability that both are even? All right, so um, both are even. If I look at the numbers from 1 to 40, I'll notice that there are going to be 20 even numbers out of 40. Now, they're regenerating this number each time, so they're not saying that once I've picked a number, that number is gone. So there are, again, 20 out of 40 different possibilities for the second value. Now, when I multiply these two things together, I could go 20 times 20 is 400, but I could also reduce both of these fractions first and say that this is a half times a half, and that'll give me, um, let's see, 1/4. All right. So what is the probability that one is even and one is odd? Now this one is probably the one that gives most people the hardest because they just want to go, well, they want to go, well, one is even, one is odd, and say it's 20 for the even one out of 40, and then 20 out of 40 for the odd one. All right. But that is only really half of the problem here. So let's break it down. For one is even, one is odd, you could have the probability that you have uh, the first even, second odd, or you could have the first odd, second even. And it's that part, this or part, that most people miss. So what is it? Since it's an or statement, these are two mutually exclusive events. So we're going to end up calculating each of them and adding them. So if you think about it that way, this first one, well, and I'm going to simplify going through what we had up here. The first even, well, there are 20 out of 40 or a half that you're going to get an even. And then there's 20 out of 40 or a half that you're going to get an odd. And then to that, you're going to add the first one being odd, which again, 20 out of 40 gives you a half. And then the second one even, again, giving you a half. So here's a quarter, that will give you 1/2. And you can think about it this way. The last possibility for this is both numbers are odd. And if both numbers are odd, all right, you again have 20 out of 20, 20 out of 20, give you another fourth, a fourth plus a half plus another fourth. That's all of the options. You get one. So um, we feel fairly confident that these are the correct answers for those two particular problems. This next one, both numbers are less than 30. Well, there are 29 numbers in this list that are less than 30. And another one is 29 less than 30. Ah, less than 30. So we get 29 out of 40 or 29 out of 40. Now that one's not going to come out very nice. So we will go 29 out of 40, and we'll hit squared there. And we'll get, oh, can I get a fraction? Well, give me a fraction. Ooh, 841 out of 1600. All right, so to get the same number chosen twice, there's only a 1 in 40 chance that you will pick that number on the first one. But once you've chosen it, you have to choose the same number again. There's not another option. So once you roll that number, it can be whatever it is, but the next one has to be the same. So there's a 1 in 40 chance that you're going to get the same number twice. Okay, next example. When going shopping at the local market, there are 15 packages of raw chicken in the butcher aisle, 3 of which have gone bad. If you select 5 packages at random, what is the probability that? Okay, let's break this down. So remember, probability is favorable outcomes over total outcomes. So the first thing we want to talk about is those total outcomes. All right. So I have 15 packages and I can choose 5 of them. It's going to be 15 chosen 5 at a time, completely random. That's going to be a pretty big number. I'm going to calculate it this one time, but I'm not going to calculate any of them individually. So 15, if I hit math, I go over to probability, I hit 3, and I choose 5 at a time. That's 3,003 different ways you could choose those packages. So the first one says you're going to select no bad packages of chicken. So the probability of no bad packages, well, if 3 of them have gone bad, that means that 12 are still good. So I'm going to go 12 chosen. Oops, let's get that right. I'm going to go 12 chosen 5 at a time over 15 chosen 5 at a time. All right. And we go and we calculate it, and I'm going to try to get a fraction, although I doubt we'll get one. So we'll go 12 math over here, just go all the way over to probability, hit 3, chosen 5 at a time, divided by, I don't want to put that, oops, I got to get back up there, I got to be careful. Be careful whether you're in a superscript or in the regular. So I'm back into my regular script there, divided by, that's my total. So second answer, hit enter, and let's see if it'll give me a fraction, although I doubt it. Oh, look at that, 24 over 91. 24 over 91, or what was it, 0.2, I missed it. 264. 0.264. Either of those will be acceptable. You select exactly one package of bad chicken. So probability, one bad package. All right, so um, I'm going to select one bad package. So since they're all indistinguishable from each other, there are 3 bad packages of which I'm going to choose one. But I still said I'm selecting 5 total. So from the 12 that are still good remaining, I'm choosing 4, and that's going to be all over the 15 choose 5, still the same. So let's do that calculation. Let's go alpha. Let's go y equals to bring up the fraction menu. And then if it can come up as a fraction, it will. So it would be, there are the 3 that are bad. We're going to hit math. We're going to go over to the probability. We're going to hit 3, and we're going to choose 1. And then that, again, you got to be careful. I did it twice now. So hit your right arrow key to bring it back up. Hit your multiply. Now we're going to go 4 over to math, probability, hit 3, hit, oops, we want this one to be a 12. All right, so let's review. There are 3 bad packages of which we're choosing 1, and then there are 12 good packages which we're choosing 4. So we get our total 5 packages, and then that we're going to divide by, I'm just going to type in that number again since it's still kind of small. 303, because that's what we calculated up here. And I get 45 out of 91. All right, 45 out of 91. You select at least one package of bad chicken. So at least one bad package. There's a couple of different ways we could calculate it. We could calculate it exactly one bad package, or exactly two bad packages, or exactly three bad packages. We could calculate all of those probabilities and add them, and that would work. But at least one bad package of chicken is the complement of no bad packages of chicken. If you pick no bad packages of chicken, then the remaining probabilities will have at least one in it. So the probability at least one is the complement of no bad packages. So all we would have to do is go 1 minus this thing, 24 over 91, 1 minus 24 divided by 91. We'll get the decimal value, and we'll get the fraction value as well. So the probability that you'd get at least one bad package out of that bunch is 73.6%. I think I'm going to leave that one alone. And it would be, let's see here, what is 67 over 91, which is equal to 0. What did I say? 736. 736. And I would not take those odds, so we will move on. And then the final one, you select all bad packages, or all packages of bad chicken. Well, that's another kind of a trick question, asking you to make sure that you read. Since I am selecting 5 at random, and there are 3 that have gone bad, there is a 0 probability that I will get all bad, because even if I get all 3 bad, I'm still going to get 2 good ones in that bunch. All right, next. Suppose there's a game of dice in which any given roll you have a 40% chance of winning. You play 4 games. What is the probability that A, you win all 4 times? Well, that would be each one you have a 40% chance of winning. So you're going to go probability win 4. That's going to be 0.4 to the 4th. And 0.4 raised to the 4th is either 0.0265 or 16 over 625. Not very good, even though you have a 40% chance winning on the first try. You win none of the games. Now, this is a little bit different. Winning none of the games is not the complement of win all 4 games, because winning none of the games does not include winning 3 times, or winning 2 times, or winning exactly 1 time. So this one is going to win no games will be the complement to the 4th. And so the complement of winning a single game would be 0.6. That's the probability that we would lose. And then we'll raise that to the 4th. So the probability that you will lose all the games, 0.6 raised to the 4th. Oops, I don't want to do that just yet. Let's go back out. 0.6 to the 4th. and go second. Math, hit enter there. We'll get a fraction. So 1 point. So there's only a 12.96, almost just a 13% chance that you'll lose all of those games. So it was 0.139, and then was it a 6 there? 1296. Sorry about that. Let's fix that. 296. And the fraction 81 over 625. 81,625. The probability that you'll win at least one of the games. So at least one includes exactly 1, exactly 2, exactly 3, and exactly 4. That is the complement of none of the games. So this one is a complement. We can say probability win at least one would be the complement of win none. So I can go 1 minus 81 over 625. So the probability that you win at least one is going to be 554 over 625, which is pretty good actually. 554 over 625, and that 554 divided by 625 is 0.8. So 88% chance that you're going to win at least one, which is okay. 88.64. That doesn't necessarily mean that you're going to win any money, all right? Because if you play a dice and it's an even, if you bet $1 and you win $1 back, let's just say it was an even game, you have to win 2. If you win 2, you're just breaking even. You have to win 3 to actually win any money. All right, last one. Let's talk about poker. And just as a quick review of poker, there are 52 cards. Okay, so last example, it's about poker. Let's review the cards just to be clear. There are 52 cards. There are 13 values for each card. So you've got 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, Ace. 13 values. There are 4 suits: hearts, diamonds, clubs, and spades. And that's it. So that's how we're going to be calculating this. And if I'm being dealt 5 cards, so my total outcomes will always be 52 chosen 5 at a time. So that's all of the possibilities that you could get. And that's quite a large number. I'm not going to be calculating it every time. So 52 math, go over to probability, hit 3 there, and we're choosing 5 at a time. So there are 2 million, or no, there are 2,598,960 different hands that you could get when you're playing cards, and you're dealt 5. So what is a probability that I get a pair? So probability of a pair. This is where this starts getting kind of complex, all right? So the first thing is you have to choose one of these values for which to get the pair. So out of the 13 values, we are choosing one value that we're going to get a pair of, okay? So since I'm talking about a pair, there are 4 different suits that have that same value. So let's say that we chose a 3, all right? There's a 3 of hearts, a 3 of diamonds, a 3 of spades, and a 3 of clubs. So there are 4 cards of which I'm choosing 2 of them to get my pair. All right, so I could get a 3 of hearts and a 3 of clubs, or I could get a 3 of hearts and a 3 of diamonds. It doesn't matter what the pair is, but there are 4 of them of which I'm choosing 2. All right, now, if I'm going to get exactly a pair, that means the last 3 cards all have to be different, and they all have to be different than that first card. So there are 12 different values left, of which I have to choose 3. And since I can't have any of them match, there are, for each of those 3 different values, there are 4 cards of which I'm going to choose 1. Now I could write that out 3 times, but it'll be the same for all of them. So I'm just going to raise that to the 3rd power, and it will be over the 50 to choose 5. Now this gets pretty long, so I'm just going to calculate the decimal value. I'm not going to worry about the fractional number. So let's just go through that here. So I'm going to go alpha. I hit my y equals. I'm going to bring up that. And so it's 13, and then math, and then I'm going to choose, I'm choosing 1 from that 13. You got to go up, so be careful. And then it's times, and then from that 13, that first value, I have 4, and then I don't want to hit alpha, I want to hit the math button. I'm going to go over to probability again, bring up that 3, and we're choosing 2 of that. And then we're going to come up again, so we're going to hit, we're going to multiply that, and then there are 12 different values left, so we want to choose 3 of those, and then for each of those 3 cards, we're going to go, I'm going to put a parenthesis there just to be safe, 4, hit my math, come over to probability, hit my 3, we're going to choose 1 of each of those, come up, hit parenthesis, and we're going to raise that to the 3rd, and then we're going to go all over 52, math, probability, so I'm going to hit 3 again, and we're choosing 5, and oh, look at that, it does give me a fraction, so 352 out of 833, and I really don't want the fraction value there, so 352 over 833 is a 42.422, so 0.424, because that last one rounds up. No, 423, sorry. So let's go back here. So 0.423. Yes, so 0.423. All right, okay, so we want to get 3 of a kind. If we're trying to get 3 of a kind, let's get the right tool. So we're trying to get 3 of a kind. We're going to go, what is 3 of a kind? We are going to go 13, and we're again going to choose 1. So that's going to be our 3. There are 4 suits that have that value. So of that 4, we're going to choose 3 of those. There will be 12 different values left, of which we are going to choose 2. And then of those 2 values, there are 4 for each of those, of which we are going to choose 1. But we have to hit square on that over 50 to choose 5. Okay. So we're going to calculate our triple, and this time, instead of using that fraction bar, because I just want the decimal value, I'm going to make it as a parenthesis for the numerator, and I'm going to divide parenthesis for the denominator. So there are 13 different values, and we want to choose 1 value for the triple. All right, I bring it back up. That 1 value has 4 cards, and so I'm going to choose 3 of those same value, and now I have 2 cards left. So there are 12 different values left because I can't have that first value again. And so I'm going to have 3, and we're going to choose 2 different values. And then from those 2 different values, I'm going to hit parentheses. There are 4 cards, of which I'm only going to choose 1 value for that. And since it's going to be the same for both of them, all right, so for both of those 2 values, I do it for choose 1 for the second card as well. So I'm going to hit squared, and then we're going to close that parenthesis, and we're going to be divided by parenthesis the 52 I don't want alpha. I just want that. 3, 5, and then we will close that parenthesis, and we will get the probability that you can choose 3 of a kind is 0.2, there we go, 0.0211. And since I have a 0 as this first one, 3 significant figures will be these first 3. So you have a 0.0211. So you have a 2% chance of getting dealt 3 of a kind. That's way lower than getting dealt a pair. So a pair is a pretty easy value to get. All right, so for the last one, they want us to find 2 pair. So we're going to go 2 pair. Now to calculate this one, again, there are 13 different values. And since we want 2 pair, we are going to choose 2 kinds to get the pairs. Each of those 2 values that we've chosen, there are 4 cards, and since it's a pair, we're going to choose 2 of those. So we're going to have 4 choose 2 for the first card, and then, or for the first value, and then we're going to square that so we can have 4 choose 2 for the second value for the second pair. Then, since we've chosen 2 of these, there are only 11 cards left. We're going to choose 1 of those, and that gives us the third value that we have. That gives us the third value that we are trying to find. And that third value has 4 cards, of which we are going to choose 1 of those 4 cards, and that will be over the 52, choose 5. Making that calculation, we have, I'm going to put parentheses again, we have 13, math, go over to probability, hit 3, we're choosing 2, and then come up, we're going to multiply. And then for each of those 2 values, we have 4 cards, of which we're going to choose 2. And since each of those has to do to choose 2, we are going to square that value. Square that. And then there are 11 different values left. And we're going to choose 1 of those. And then in that value, there are 4 cards, of which we need to choose 1. And then we'll divide that by 52, math, choose 5. Let's see here, that's not the right one yet. Choose 5, close my parentheses, hit enter, and we get 0.475, which is clearly better than this one, but still pretty small. 0.0475. And again, that's still pretty small. You know, getting a pair was almost 50% chance. Get 2 pairs, you go all the way down to a 4% chance, and then to get 3 of a kind, you go down to 3% chance. So the values get fairly short very quickly. That's all I got for today, folks. And so the Star Wars fun fact of the day: in Return of the Jedi, to make the speeder bike chase scene look like it was going 120 miles an hour, a Steadicam operator filmed in a California redwood forest at a rate of 33/4 of a frame per second and moved very slowly. Then when the film was played back at normal speed at 24 frames a second, it gives the illusion of very fast movement. That's all I got for today, folks. Have a good day. Bye.